Hi guys, welcome back. So in this video we will be talking about anti-debugging techniques. If you have watched the GDB video, I suppose you have dealt, or let's say you have learned how to debug programs and just say understand how programs are actually built. Now, one of the few let's say features that can be added to the software is actually one of the anti-debugging techniques that can prevent reverse engineers from debugging your software. I will be talking also at the end of the video about a concept called patching. So patching is a way to destroy anti-debugging techniques. So in this video, we will be just talking about some basic stuff. We won't be going further, or just let's say more complicated anti-debugging techniques. I will be just talking about one anti-debugging technique in this video, uh, which will involve the usage of a function called Ptrace. Now, just to explain briefly what anti-debugging techniques in real life. So imagine just having some developers that will be creating some software and actually just involving the fact that they will be trying to use their own debuggers from a high level perspective just to find out and just to find out and fix the mistakes and the bugs in their code. It's just like, for example, looking for the errors um, that would happen inside of the code. Now, just imagine some other hackers who are trying to um, use the same debugging skills just to try to figure out the intricacies of the software itself. So they might want to figure out, for example, how it works, how the encryption is happening inside of your software, how, I don't know, for example, the serial keys are generated inside of your software, etc., etc., etc. So anti-debugging techniques, guys, are like some secret, let's just say, guardians to the software that you have built, and they try to stop these hackers from easily just figuring out what's going on inside of your program. So it's just like actually not stopping them from cracking the software, but it just makes the process harder from the usual process that we have done in the previous videos. So in today's video, guys, we will be working on a challenge that I have created specifically for this purpose. This challenge comes from a local CDF that happened in my university, and I thought it is a great opportunity just to showcase how anti-debugging works from let's just say from a basic perspective or system basic stuff. No worries, guys. You will learn something new if you haven't just let's just say saw an anti-debugging technique before. Yeah. So we start by seeing what is in the folder. So we have a binary. We do the usual stuff. We try to see what is what is the information that could be extracted from the binary. So it's for Linux, obviously. So it's dynamically linked. So this is the interpreter, okay, and it's not script, okay. So if we run strings on it, so if we run strings on the serial killer, we see that we have some usual stuff. So it's some usual stuff. So if we try to run it, she said that the usage is the name of the binary and the serial. Okay, so what do we have? Let's say we have a serial which is file. Let's say for example AD2, let's say 2. This is some random. Okay. He said nope. Now, one of the few things that we have learned along the way is that when we try to reverse engineer any kind of binary we either try to use a tool that exists or we try to use GDB. Now, if we try to use GDB on that binary, we see that the GDB is now working. But if we try this, let's just try to do the usual stuff just by trying to see what functions do we have. So if we call down info functions, we see that we have the main. So if we break into the main and try to run the binary, we see that he um, we got the breakpoint, or we hit the breakpoint. Now, before doing the breakpoint, I want to see something, or I want to showcase something. So let's try to see the info breakpoint and try to delete that breakpoint and try to run again. So if we run again, guys, as you can see, if we have run the same binary just out of the GDB, we got the message nope. But if we try to run the same binary from the GDB, we get another message, which is really. So that message actually, guys, means that we are actually, the program have noticed that we are using a debugger. So this is, guys, actually an anti-debugging techniques, and you will see eventually how this anti-debugging techniques has an impact on the process of trying to reverse engineer this binary. So for example, now let's try to go back and set another breakpoint as we have done, and we try to run. Now if we try to, so this is just the usual stack preparation as we have talked in the previous videos. Now we go back, so we keep stepping, and then we actually hit a function called Ptrace. Now, if we try to go into this Ptrace, now we are in the Ptrace. If we try to finish down um, the execution of Ptrace, he is now comparing the result of the Ptrace with a value. And then he is going to compare that value with this value, and based on the conversion that will be happening, he will be going to jump into some other places, or some other place in the code. So if not, if we jump if not equals to this address in the code. Otherwise, we get into this section. So if we try, so he's calling the puts function that will be printing some message for us. So if we go back and try to see what this message is, so this is the address of the string that will be printed in the screen. So we can just see the content of that message using the x dash s, and the message is really. Now if we try to step, and then we step, and we finish from the put, and then as you can see, he will be eventually just jumping to the main plus 208, which means that the program is trying to exit, which means that if he detected a debugger, he is going to exit. And this is, guys, basically what anti-debugging is when you try to deal with it. So he is not going to let you debug the program the way you want. So this is basically what anti-debugging is. Now, what's really interesting, guys, is how can we defeat such a technique? So this is basically what we need to learn in this video. So just to do that, we can just break down the comparison, or we can just use another technique called patching. So we try to patch the instruction, and we will try to see that at the end of the video. Now, if we try to go back, um, let's say try to run the program again. So we will be stepping back to that call. But before we step back to that call, we need to figure out what the ptrace is doing exactly. So we cannot just ignore the ptrace and try to let's just say trick down the conversion without just figuring out what the ptrace is doing. So let's just make a quick search about the ptrace, obviously. So if we do ptrace, we see that The bit-trace system call provides a means by which one process, the tracer, may observe and control the execution of another process, which is the tracee, and examine and change the tracer, memory, and register. It is primarily used to implement breakpoints debugging and system call tracing. So that means that the bit-trace um, can help the developer track down, um, let's say, the breakpoint, or let's say the system calls of tracing, which means that this is actually what the bit trace is taking. So this is the request, the PID, the address, and the data. Yeah. So that means that before the if we run again, we see and we step. So this is basically what the bit trace is going to be having. So he is passing down some parameters to the bit trace, and then he is calling back, or he is calling the bit trace itself. So that means that once he passed down, or he passed down those parameters, he will be trying um, to trace to trace the actual program. So for example, if he passes down the ptrace trace me, that indicates that this process is to be traced by its parent. So a process probably shouldn't make this request if its parent isn't expecting to trace it. So that means actually, guys, that once we have called the ptrace, that means that an anti-debugging technique is involved in the binary that you are working on. So now, just to do that, we don't have to deal with the ptrace as a function that we should understand let's say, each detail about it. We can just deal with it as a black box, and let's just say that the ptrace is the one that will be helping the program to detect if a debugger is involved or not. But if we go just a little back and we try, for example, to call it, and then once we finish, we see that he is taking some result, which means that the bit trace, since as we have talked, the arrax is storing the result of any kind of function that was executed, which means that the result of the bit trace function is now into the arrax, which means that he is going to compare the result of the bit trace with that value. And that value actually, guys, is -1, but it's in the hexadecimal format, and it is signed. That's why we are trying actually, we are seeing 0xFFF, which this is actually equivalent to -1. So he is comparing the arrayx with -1, and then once that value is not equal to -1, he's going to be jumping into another block of code. Otherwise, he will be just printing for us the message really, which means that this block is used for just showcasing that, okay, you are captured and the debugger is captured. Otherwise, we just pass down and we go into another block, which is actually the main program. So now if we trick down these two instructions, we should be able to jump into that address. Now the question that is really interesting: how can we trick down that um, that conversion just to go into this instruction? So we should just set the arrayx different to that value, and once we do that, so if we just compare the arrayx with that value, um, and they are not equal now, we should be able to do that. So if you just go back and see that the arrayx now is equals to that exact same value. So if you just try to change the arrayx with another value, the conversion should be not equal, and he will be jumping to that address. So to set that, we can use that into the GDB by setting the arrayx to some just random value. Let's say 1. And if we do now info registers, we should be just seeing that the arrayx now is containing 1. Now, once we step again, we see that he is going to be comparing the two values, which we already did, and he will actually now jump to that address. Now, if we take that, we see that he has taken that jump, and we have bypassed the call of the ptrace, which means we have actually bypassed the ptrace. And despite using a debugger, we have bypassed the anti-debugging technique. Now he is going to be comparing the RBP minus 0x24, which contains the argument counter in the C program, and he is going to be comparing that with you. And since we haven't pretty much passed down any parameters to the program, he will be taking that value just to the message of the usage, I suppose. If we just take a look, yeah, it's the usage. Now, if we run again the program and just passes down any kind of parameters, let's say item byte, now, and we complete and we step, and then we get into the Ptrace and then we finish, and then we patch down, let's just say we bypass down that conversion by setting the array_x equals to 0x1, and then we step again. I suppose now the conversion will be okay, and now we are actually in the main program. Now this is actually, guys, really interesting, since we have now bypassed the technique that was implemented by the, let's say, the developer, just to prevent us from doing the debugging that we want. Is actually really interesting. Now he is trying to move something into the EDI, and then he's calling the S random. So the S random is used as a seed. So for who do not, for you guys, if you don't know, the seed is something we use to make the random function generate numbers based on the seed. So for example, if he is now trying to pass down this number as a seed, the generated numbers will be using that seed to generate, let's say, numbers, because random numbers is actually a big or a huge word, because once you, let's suppose you are passing a seed which will be equals to 1, and you execute the program once and twice, and let's say multiple times, you actually got the same random numbers. So actually this is a kind of vulnerability in the code, because once you hard code the seed, you actually don't have any random numbers again. So you actually have just some plain text numbers, because I can generate them on myself too, and anyone who is having some Linux should be generating the same numbers too. So yes, so this is basically what is happening. So now if you go back, so he's calling the S random. If we finish, since we are on the S random, we finish and then we go back. Now he is calling some other function which is called generated serial. If we just try to disassemble this function, we see that is a function that is going to be generating some serial. We don't have to reverse engineer this function statically. We can just take the value returned by this generated serial, since he is passing some value in this some parameter, let's say, to this function. He is going also to pass down that to the generated serial, and then the generated serial actually, let's say what this generated serial, or let's just say what is the purpose of this serial exactly, just by keeping on stepping. So we step, and then he is going to compare what's actually, let's suppose, as the intended serial that was passed down to the program with the generated serial. Now, if we look into the RSI, we should be having some value. So yeah, so I suppose this is the intended serial. And if we go and take a look at the RDI, we should be having our um, actually the array_x, I'm sorry. If we take a look at the array_x, we should be having, yes, our input. So he is comparing item byte with that serial. So if we now try to take that serial, so if we try to take down that serial, so he is going to be testing something. Now he is taking that value. I suppose this is the nope. Uh, yes, this is the nope. Now if you try to just to exit now the GDB and try to use this serial, we should be just okay, I suppose. Okay, I think I have called, yeah, yeah. So you got it. Now, this is a way just to defeat anti-debugging when you try to deal with any kind of binary that you would be having. Now, another interesting just usage is we don't have to always just run the program and try to just set the arrax or just try to break down the conversion just manually. We can just patch down the whole binary, and specifically we can patch down that instruction. For example, when you do, for example, that, and you break into the main, and then you run, and then you step. We don't have to just always break down these two instructions. We can just patch down the jump if not equals to just jump if equals. If we make this jump if not equals to jump equals, so that means that we have to break the logic of the program, and once he will be detecting a GDB or just some debugger, he actually will be executing the main code of the program itself. So to do that, we can just use Ghidra, for example. To do that, we can just drop down the binary. Just to do that, Explorer, we can just drop down the serial killer to this place and just patch down directly. We can also use hexdamp to do that just by trying to find out where that jump if not equals is in the binary and patch it down. But actually, I think Ghidra is a lot easier to do that. Just it's just another opportunity for me just to showcase the usage of Ghidra. So once you have loaded the program, you'll be having a lot of stuff in here. So mainly this is the assembly of your program. This is where the compiler is living. This is the defined strings, the kind of strings that exist in your binary, and this is where we will be dealing with the functions. So this is the imports of the binary, this is the exports that we have talked about in the previous videos, etc., etc. Now we will be jumping to the main, and I will be trying to see the compiled code with you. So we have the bitrace as we have talked. So this is the bitrace trace. You can just take a look at the documentation of the Ptrace. If you don't have what the Ptrace trace is doing, it's an opportunity for you just to check the documentation whenever you try to reverse engineer any kind of code. Now, one of the few things that I have been doing always when trying to reverse any kind of code when using the decompiler is just to unname the function that exists. So this is basically the argument counter. This is the argument vector. Let's suppose this is the answer of the bit race. What else do we have? So if the answer of the bit race is equals to -1, so this is the 0xFFFF as you can see. He will be printing really, and this is, I suppose, the return of the main. So it is a 1, okay. So if the answer of the bit race is equals to -1, then he will be printing really. Otherwise, if the argument count is equals to 2, then he will be generating some, so he will be first setting the seed, and then he will be generating some serial. So this is the serial, I suppose. And yes, it is a table of characters with a 32 character. Yeah, then he is going to be comparing the result or the argument vector of 1, which means the parameters that will be passed to the binary with the serial, with the generated serial, I'm sorry. And then this is the answer, let's say check. So if the check is equals to 0, then you got it, otherwise it's a nope. Otherwise, he will be setting the usage of the serial and the argument vector of 0, which is the name of the binary. Yeah. So now what's really interesting is that this instruction or this line is the GNZ, which means that if it is not equal, um, then he will be just jumping to this location. Now, if you try to patch down something using Ghidra, you could just go and use the patch instruction. So instead of a G and Z, we'll be using GZ. It's the opposite of a G and Z, which is the GZ, which means that if they are equals, which means there is a debugger, then despite having the debugger, we will be executing the main code of the program. Now, if we do GZ, as you can see, the flow of the program has changed, and now instead of just comparing if the debugger exists, and then once we detect a debugger, we will be actually executing the main program of the program itself. Yeah, so we'll be executing the main program. So to export this, we can use File and go into Export Program, Original File, and yes, we have now the file. I suppose now if we go into that file, I suppose if we do just ls, we should be having a new binary, and this is actually the patched binary, just to check that out. Yes, it has the same thing, but now once we have patched the binary, one thing that we can check out if the binary has been patched or not is just by seeing the flow of the program. So now if there is a debugger, then he is going to execute the program, otherwise he will be putting really. We have inversed the logic of the program itself. So now I suppose if we try, for example, if we try just to run the program outside the debugger, we should be getting the message really, as you can see. Now, if we try to run the program from a debugger, we should be getting the message usage serial coder, which is serial. Now we have inversed the logic of the program, and now I suppose with this binary we can work without any anti-debugging techniques. And we have actually destroyed the anti-debugging techniques which been placed using the Ptrace function. Yes. So this is basically what I have tried to explain for you in this video, and this is actually a pretty basic anti-debugging technique that exists. And what's really interesting, guys, is that there are a lot of functions that we can work on too. So don't forget to follow me on Twitter, and don't forget to subscribe to, and goodbye in the next video.